a bit of introduction to this. As some of you know who've been to Casper workshops before, and I guess half of us haven't been to one of these before, as far as I know, there has not previously been an educational part at the start of the meeting. And so, starting in discussions in China, and since then, in the advisory board, I assume, I'm not on the advisory board, and then in the organizing committee, we've built into the program the idea that we're going to spend a couple days trying to take the very high level information of the meeting and reach down at the start and pull some people up. And part of that is, securing money to bring to pay people's travel costs to the meeting. Part of that is this PIRE thing. You've seen that in the name. PIRE is an NSF program, with Partnership for International Research and Education. There's one that is EHT related, the Black Hole PIRE that SAO, Arizona, Harvard, Asia A, and Taiwan, a couple organizations in Mexico are part of. And as part of it, we have some digital signal processing work that involves Casper tools, and we promised to do educational aspects, and so we sort of married these things, and that's why the PIRE is generously included in the name of this Casper workshop. So all of that said, it is one of the more humiliating moments of my life to have to stand up here and tell these people about radio astronomy. I'm willing to do it because I think that that's a good idea, right? There are people here who are new to the community and new to the research area. There are perhaps, maybe, probably not, but I can dream, some engineers who feel like, boy, I wish someone had once told me about radio astronomy, this thing I work on all the time. But anyway, I have to do it, and I will do it, and I hope that people find this beneficial. I certainly will not be offended if people who've spent their entire lives doing this are working on their email while I'm giving this talk. But again, this is not aimed at my advisor who taught me radio astronomy 19 years ago or something like that. So with all of that said, let me begin. Reaching down very far, if you are interested in bringing yourself up to speed on radio astronomy, a 40-minute talk is definitely not going to cover you. So I just want to point to a couple of resources that will appear in my slides when appropriate. ERA for Essential Radio Astronomy. This is a textbook that's relatively new. A lot of that textbook is available online if you just Google NRAO ERA, because it started as an online web class that was taught at University of Virginia and then was made into a book. The other resource, which is the Bible for interferometry, is Thompson, Rand, and Swenson. Rand is here. In the latest edition of this book, people may not know this, but this is an open access book. You can download this for free. You don't need to have a Springer subscription. And if you have any interferometric questions, the answer is definitely in there. And both of these things will appear in the corners of my slides in these two talks. But I encourage you to seek these out. There are many, many books, but these are a good place to start. Okay, let's talk about radio astronomy. Radio astronomy is the second branch of astronomy, right? Obviously, astronomy started with visual wavelengths. But before we could get above the atmosphere, the other place that we could make progress was this radio window. This is the height at which the atmosphere absorbs the radiation, and you can see there's this narrow visible light window, and then the infrared where our eyes didn't evolve to see, and then there's this vast radio window, 5 decades of frequency. And a whole bunch of different phenomena occur in this window, and we can study through radio astronomy. Of course, we can go above the atmosphere now. We've studied all of these wavelengths, but thanks to technology developments preceding and during World War II, there was a good start, and at Bell Labs, communication technologies, there was a good start in this window that before we even got to space, and it was a long time before radio astronomy moved to space in any case. The bounds on this window come at the high end from the water vapor in the Earth's atmosphere. So This is a plot of transmission over 3.5 to 2.5 decades of frequency. Starting at 10 gigahertz, below that, the atmospheric behavior is not very interesting. And going up to 3 terahertz, you can see these are plotted for very favorable conditions at very exciting places on Earth. There's very little transmission. This red line, for example, is Kitt Peak. It is a historic radio astronomy site. It's where Bob measured carbon monoxide molecule for the first time. It just barely squeaks out any transmission in some of its best days of the year. But in principle, there are places on Earth where you can see up to 1 terahertz and beyond. The thing that's cutting us off is water vapor, but the other interesting features here, like this, are oxygen in the Earth's atmosphere, which you can't avoid no matter where you go. These narrow lines tend to be ozone. All right, so the low frequency end, you'd think the radio window should extend down to 0 frequency. It doesn't. That's because there are free electrons in the Earth's ionosphere, and the plasma frequency is of order megahertz. And below this plasma frequency cutoff, there's total internal reflection in the Earth's atmosphere. And so we can't see out, and radio waves can't make it in. And even above that cutoff, the atmosphere, the ionosphere is a source of real frustration. It's a shimmering refractive screen that distorts the low frequency view of the universe and leads to difficult calibration problems for all the very interesting low frequency instruments that are going on. Many of you are involved in them. This is just an example of position shifts induced by the ionosphere using MWA data. Does this work? Ooh, it does. Okay. All right. So radio astronomy gives us from, say, 10 megahertz, maybe down to a few megahertz at nighttime, up and low solar activity, up to as much as 1.5 terahertz from the ground. But the thing that defines radio astronomy is not necessarily just that atmospheric window, but it's a set of pretty common attributes for the way that we do sensing here, different than what people are used to in optical astronomy or other wavelengths. So the first of these is that the systems we use to receive this radiation tend to be a small number of wavelengths across. If you think of an optical telescope and being 10 meters across at 1 micron wavelength or shorter, that is a lot of wavelengths, right? That's 10 to the 7 wavelengths. If you think of a radio telescope, some of the telescopes we use are sub-wavelength. The feed horns, the waveguides we use are sub-wavelength sometimes. The waveguides always are. Or not always. And so this means that we have to concern ourselves with diffraction. In fact, ray tracing your radio optics is not usually what we do. We have to consider the way the beam will expand as it propagates. We have preposterously large photon counts, and so nobody is counting photons. We tend to interact with the radiation we're sensing by coupling to the electric field rather than collecting photons in a bucket. The fact that we can couple to the electric field gives us access to techniques that are enormously useful that I think at any other wavelength we would love to have. We can quite easily shift the frequency of the radiation we're detecting at our convenience. So we can move it to low frequency where electronics are more functional. We can provide gain to our signals. So I will talk about interferometry in my second talk, but in interferometry we receive the electric field from the universe. We multiply it, we can split it up into many paths, and we can multiply it against each other. The equivalent technique in the infrared is a series of diminishing return splits of the exact same photons. There's no gain to make those photons back up, and interferometry is much harder that way. And of course, the reason we're all here is we can digitize the electric field waveforms that we put on our wires from our antennas in order to do cool tricks with them. We can do very simple things like just making a spectrum by taking a Fourier transform. We can do, more complicated things like multiplying the signals from two antennas, or summing the signals from different antennas to direct beams in different directions on the sky. And so, I hope that in this talk I start to set up some of the things that will be covered in later topics that will build you up, if you're new, to the point where you're ready to absorb the tidal wave of advanced DSP ideas that will hit you Wednesday through Friday. All right, so another thing, though, that's somewhat unusual is that we are usually swamped with noise. Our detectors are generating noise. Everything is emitting noise thermally at these wavelengths, the telescopes, the atmosphere, the ground. Even sources out in space that we don't want are glowing in ways we wish they wouldn't be. For example, if you're working on low-frequency radio astronomy to see the epoch of reionization, the glow from electrons spiraling around the magnetic fields of the galaxy is a real pain. It's an enormous foreground signal that you have to see through to see the signal you're interested in. Radio astronomy is not yet 100 years old. It began at Bell Labs with Carl Jansky looking for where static was coming from in shortwave transmission. I assume Bob will cover this because the same picture appeared in the poster for his slide. But basically, Jansky spun this giant 20 megahertz antenna around, noticed that there was preferred directions for radiation that rotated at not just diurnal rate, but sidereal rate, so it wasn't tied to our day, but was tied to beyond the solar system. Noticed that the brightest emission seemed to come from the center of the galaxy. Going on, Gert Reber heard about these results. Jansky published a few papers in radio engineering journals. In his backyard, built this antenna and started mapping the sky. You can see very strong modulation in the signals he was seeing here. This is a strip chart recording of this data. Here's a map of the sky. He discovered famous radio sources that we still use those names today, including the center of our galaxy and a radio galaxy and supernova remnant. I include this just because it's here, but the first radio spectral line was measured on campus. We're not quite on Harvard's campus, at least that's, I think, true. But down the hill, the physics building, this was stuck out of a window, and there's a whole set of equipment in there. And here's Doc Ewan by the horn, and the prediction that there should be a spin flip line from neutral hydrogen was made just before they decided, all right, let's go try and make this measurement, and they found the line, and the other groups followed up, and this line has been an enormously important line for understanding the astrophysics of galaxies ever since, and our own galaxy for that matter. Transients. The first pulsar was, of course, discovered in the radio. It was discovered in 1967, and eventually, after a lot of determination, the discoverer, Jocelyn Bell Burnell, convinced her advisor of it, and he published a paper as first author and got himself a prize and so on. That's a well-known story. These things have been, there's more than 50 years of pulsars now, and it's an ever-growing field and continues to be interesting for astrophysics reasons and for fundamental physics reasons and for just a whole host of reasons. And transients themselves, other variable sources, rapidly varying sources, are motivating many of the people in this room to work on these problems. All right, so just a brief overview of the things that emit in the radio. So we have synchrotron radiation, which is the radiation of electrons going around magnetic fields. We have free radiation, which is the radiation as electrons are accelerated by interactions. There's the thermal glow of dust that's ubiquitous in the universe. It conveniently has a very steep spectrum, so as you go to high frequencies, this becomes increasingly dominant, and it's the reason that our high-frequency radio interferometers tend to study the dusty glow of the interstellar medium, but the low-frequency ones can't possibly see it. There are lines from molecules. Carbon monoxide is the second most abundant molecule in the universe, and it's our best tracer of the gas that forms stars. Atomic lines, hyperfine transitions. There's very little photon energy in the radio, and so the only things that can, the only transitions that can produce radiation are not the things you're used to when you learn about your hydrogen atom in high school physics. There are exotic things. Spinning dust was a theorized emission process that that has, more or less been accepted now. But 10 gigahertz-ish radiation from the spinning of dust grains. There's the thermal glow of surfaces. So black body emission, in particular, any planet you look at, the telescope that you're looking with. And the surface of last scattering of the Big Bang all glow as black bodies. There are microwave lasers. There are these pulsars I just mentioned that are spinning lighthouses that are magnetically beamed. There are other transients that are emitting radio waves in ways that we don't actually understand. And so there's a whole store of things from very energetic to very mundane and cold that you can study at these wavelengths. The telescopes that are used to study can look, significantly different, right? We have arrays of telescopes. This is ALMA in Chile. We have weird off-axis things. This is the South Pole telescope. Other weird off-axis things. This is Meerkat, and on-axis things with phased array feeds. That's ASCAP. And then, even stranger things as you go to low frequencies. This is LOFAR. This is not something that the average person would identify as a telescope, but they are dipoles arrayed and combined to see the sky. And things that don't look like telescopes at all. This is the other type of LOFAR antenna, but in there, inside each of these protective tiles is a cross-dipole antenna. The ways we use these things determine the structures, and so I think that across some of the talks you'll get to learn about this if you don't know about it. But of course, there are many resources available that I pointed to earlier. Okay, with the second half of this talk, let's talk about some basic physics that we'll need to understand radio astronomy. In all of astronomy, but I think this gets talked about most frequently in radio, we are trying to map the intensity distribution across the sky. Specific intensity is a technical term associated with, the spatial distribution of radiation, and you can construct its meaning by asking yourself how much energy is coming from a narrow range in frequency from a particular patch of sky of solid angle d omega, landing on a infinitesimal projected area, so the area normal to the direction of radiation propagation, that's what the cos theta is for, within a time dt. So that total energy is some quantity I nu, which we're defining, times this area, solid angle, time, and frequency range. So dividing that out, I knew this specific intensity or brightness or spectral brightness is the power, the energy per time, per area, per solid angle, per frequency. And the units on this are watts per meter squared per hertz per steradian. This is not the unit that's most directly, most famously associated with radio astronomy, but it's one of the two central units we use to describe the sky. This is the one that is equivalent to what we call brightness temperature, and I'll circle back to that by near the end. So brightness is useful because it's conserved along array. It's not obvious, I guess, if you aren't thinking about it, but if you have a source that's further away, you think it gets less bright, but what it actually does is get less fluxy. It's further away, but its solid angle is smaller, so the ratio of flux per solid angle is preserved. This is also useful in studying gravitational lensing, the fact that you can't change brightness. When you think about what brightness is, you can take this picture where your detector is a patch of land of area d sigma, and the source is a patch of sky of area d omega, but you can think about the reverse process just as well, where the source has a surface area, say it's a star, and your telescope is some small angle subtended at a distance, and you're integrating over the surface of the star in order to figure out what you want to figure out. Because the quantity is conserved, it doesn't really matter which direction you look at it from. If you think about your maps of the sky, they're most naturally a distribution of brightness as a function of position on the sky. Because unless you know the distance to a source, thinking about it as a map of luminosity doesn't make a lot of sense. I guess you can also think about it as a map of flux density, but we haven't covered that yet. Flux density is the emission from a source at fixed frequency integrated over the entire source. And so if you just take this brightness and integrate over your source, you end up getting rid of the steradian part, and you have watts per meter squared per hertz. This is where we define a radio unit, and this is where you realize that radio astronomy deals with small quantities of radiation, very, very faint emission, because our unit of flux is the Jansky, and it's 10 to the minus 26 watts per meter squared per hertz. Yeah, so in order to detect signals that faint, we need large apertures, we need gain, we need low noise detectors. It's a challenge that many of you are intimately familiar with. So flux density, unlike the brightness, is not conserved. It is something that decreases with the square of distance because you've integrated over the solid angle. But if you think about it, in most cases, not most, in many cases, you're not so lucky as to spatially resolve the source you're looking at, right? And if you are not resolving the source, then effectively you're doing this integral. You're detecting the integral of all the emission from the source. And so when you're measuring the emission from one of these sources, single-dish radio astronomy often expresses the detected power as a brightness temperature, but that's a unit of convenience. The thing that you are most directly measuring is the total flux density from that source, the source integrated emission. It's also more natural to speak, I feel, of detecting flux density in interferometry because the interferometers, as you'll hear about in a couple talks, are measuring a range of spatial scales simultaneously, and so and each baseline in the interferometer is not uniquely identified with a specific solid angle, and so it's hard to speak of brightness when you can more easily speak of the total flux sensed on that given spatial scale. So another really key topic in here is the emission of a black body. A thermal source in equilibrium with its surroundings has a very specific glow. It's famous in physics. This is its functional form. Even though it's just a brightness or a specific intensity, it gets a special symbol because this is such an important equation. In a longer lecture than this, you know, I would, in class or something, a radio astronomy class, I would probably derive it, but essential radio astronomy can go through the classical derivation of this and the modification to get the Planck law. That's what this is called. But for radio astronomy, we generally are not dealing with this Planck law in its full functional form, because we are most often dealing with photon energies much less than the thermal energy. For reference, if you want to know whether you're much less than the thermal energy, these two fundamental constants correspond to 21 gigahertz per Kelvin. And so, you know, the cosmic microwave background radiation on its own, about as cold as you're allowed to get in the universe, puts you at 60 gigahertz. So in this case, in this low h nu over kT limit, you know, this expands to 1 plus that, minus 1, and you end up canceling a bunch of constants, and you get this simpler thing, this 1 over lambda squared behavior, or this nu squared spectrum that we're very familiar with. Black bodies in the radio tend to be nu squared power laws. One final interesting feature for this, every physics class I had in, you know, before doing radio astronomy taught the Wien displacement law as a wavelength equation, 3 millimeters per Kelvin, or 3 millimeter Kelvin. But that is not in the per frequency units that we're used to. If you want to figure out where a black body peaks in flux density units, in Jansky units, in watts per meter squared per hertz per steradian instead of per wavelength unit, not per steradian, you need to use the radio version of this, and that is that the black body is peaking at 59 gigahertz per Kelvin. So let's use this point to bring us closer to where we need to get. So things glow thermally, but in our circuits, things also glow thermally. And so if you imagine a very simple case of two resistors connected by a long pair of transmission lines, above zero temperature, the thermal motion of electrons will create random weak voltage across these resistive terminals. This is called Johnson noise. If you have a circuit like this, then the only voltage waveforms that can persist are the ones that have nulls at the end of these transmission lines. And so you can calculate exactly what states those standing waves can have. And basically, you have to have the length of the transmission lines be an integer number of half wavelengths. And so you can convert that to frequency and count up exactly how many allowed modes there are per unit frequency. Now, the number of allowed modes per frequency sounds like a spectral density, right? It's a number of states, which we're about to turn into energy, per hertz. The way we turn it into energy is that we know that the average energy per mode in this thing from the Boltzmann distribution will be kT, the temperature of the system. And also, if we note that we want to get the number of modes in terms of a density, we need to know how to convert from wavelength to frequency, which means that we need to know how fast the modes move down the line. But if we do that, we can combine these things, the average energy per mode and the density of modes, to calculate the energy per frequency. If we then divide that by how long it takes power to transit across this line, we can get a power per frequency. Power per frequency is, watts per hertz. And it resembles the watts per meter squared per hertz and per hertz per steradian, these sort of units that we've had before now. What you get out of this is that the power in a resistor, just due to this thermal noise, is 2 kT, but there are two resistors, so it's kT. This power is a white noise, if you will. We call it white noise because it's spectrally flat. And at least at low frequency, this is effectively the Rayleigh-Jeans limit of, just like in the black body that I showed you here. At low frequency, you have this very simple equation, emission proportional to nu squared. Here, it's independent of nu. Conveniently, it's also independent of what the material is. But this is a thermal glow in our circuits. Why did I go through this? So what we do in radio astronomy is couple power from the universe onto our wires, right? We will then do things to that power from the universe. There's an electric field that was on our telescope, and now it's on our wires. We can amplify it, we can mix it, we can digitize it. The reason for thinking about the noise power in a resistor is that we can hold a resistor in our lab and we can put it at a known temperature T. And so we can tie the power that we see from our antenna to a physical temperature in our lab. And so, this sort of calibration thing has been fundamental to understanding what we're actually measuring in radio astronomy from almost the beginning. If you think about defining an antenna temperature by referencing it to this physical temperature you have in the lab, you can do it relatively easily. The flux density of a source times the effective area of your telescope, so watts per meter squared per hertz, times the number of meters squared you're collecting with, is a quantity. Now that we know this equation here, we can take the same, take this temperature, call it antenna temperature, and equate that P with that P, and you get that the antenna temperature is a flux density times the effective area over 2K. So we're tying what we measure in flux density to a physical temperature, and we can use that to ensure that we know how much power there is arriving at our antenna. One more thing to get through, I'm right on time, Jonathan, is the sensitivity of a radio telescope system. So if you think about the very simplest model of what we do in radio astronomy, we take light landing on an antenna. We select some frequency range, we pass it into something that will square its voltage, and then we average that over time. We're squaring its voltage because, remember, we've got effectively random noise coming in from the universe. There's not some waveform that we're trying to capture from the universe. This is random fluctuations. And as we just saw in the resistor, the measure of power is how big those random fluctuations are. And V squared over R is your power. You need to square it in order to get it into power units. If you think about what you might see on a wire, after going through this bandpass filter, you will see the voltage randomly oscillating around 0. It's mean 0, but the width of this distribution tells you something about the square of the width of this distribution tells you something about the power arriving. This is a histogram of the distribution of voltages you might measure. And this is something you can take directly out of your DSP processing system if you've digitized the incident radiation. As we step through this chain, though, the next thing we're going to do is square our voltages. And so that mean 0 waveform goes to something that's obviously not mean 0 anymore. You've squared the thing, and so the minimum is 0, but the distribution now has this very large tail. The average of this squared voltage is a good measure of the power in the signal, but the the root mean square width of this thing is quite large. And so, you know, it's square root 2 times whatever that average voltage is. This does not look like a nice measure of the power in the way that this does, right? We all like to see bell curves. This seems like it should be a much better way to sense what we've got here. But then let's go to the third thing. The thing that saves us in radio astronomy when we're measuring power is that we can use the central limit theorem, right? You've got, at any instant, your voltage will be somewhere in this histogram. But if you average just 50 samples and take lots of different sets of 50 samples, they'll come back into a histogram that starts to resemble the sort of normal distribution that we like to see. It's centered on the right voltage, and its width is narrowing. If we go to 200 samples, it's even closer. In fact, the number of samples, the width of this distribution is inversely proportional to the square root of the number of samples. The number of samples we're getting is this product here. This is fundamental to measurement in radio astronomy. It's the product of the bandwidth and the integration time. And so the uncertainty we have in our sample is the uncertainty in one sample divided by the square root of the number of samples, which is this pretty standard sensitivity equation we call the radiometer equation. It's the size of the temperature fluctuation or the voltage fluctuation, voltage squared fluctuation, divided by the square root of this bandwidth time product. From here, you can launch into whatever radio astronomy measurement you want, although there are perhaps a few more steps that need to be filled in along the way. I think that's it.
Wow.